I'm giving a few seconds to the rest of our registrants to maybe join us. But for those of you that are already here, welcome to today's webinar entitled Discovering High-Dimensional Biomarkers Using Statistical Shape Analysis. We are very excited to have you here and thrilled to share our work in this domain. I'll start by introducing myself. My name is Beatriz Paniagua, and I'm Assistant Director here at Kitware, and I'm joined by Jared Vicory, that is a Principal Engineer also at Kitware. We are both from the medical computing team, and this is a team that provides DevOps and research and development services to a variety of different customers. So I wanted to share a few logistical details before we move on, also giving a little bit more time to the rest of our audience to join us. But we are going to follow up this webinar with a recording of the session. So everything that you're going to see, we are going to have a recording of alongside the slides as well. So you have everything you need to share with your team or to keep for later. So you don't need to take any notes. You're going to get everything you need from this presentation after we're done. During the webinar, we're going to be monitoring the Q&A section. So is the fourth icon from the right in your go-to application. It has a little like dialogue with a question mark. Feel free to write questions there. We're going to be monitoring it frequently, and we'll do our best to answer them. Also, at the end of the webinar, we're going to have a live Q&A session. So anything that you have plenty of opportunities to inquire about the content you're going to see. Also, if you would like to contact other attendees, you can use the chat feature of the go-to application. And then the only disclaimer about the Q&A session is that if we receive a large volume of questions, we're going to address only the questions that are basically interesting to the broad audience, not anything specific. Do not worry, at the end of the webinar, we're also going to provide information and how you get, you can reach us if you have any more specific questions. So with that, let's get started. So as I said, we're working at Kitware. Kitware is a leading provider of software services in research and development consulting to a large number of different customers in industry, government, and academia. We have offices across the US and one office in Europe. We're about 200 employees. The pillar of Kitware's business model is our commitment to open source science. We have a large number of platforms that are completely free to use and that can be contributed to if you're inclined to that. But also we use those open source software solutions to provide highly custom enterprise software services to customers that so require. Next slide. So we were talking about this open source platforms, and here's just an example of some of them. There's a large number of them that serve different purposes, from medical computing to high performance computing and scientific visualization. A few of our more popular platforms are, for example, CMake, that is an open source platform that simplifies software compilation and management. We also have very popular VTK and ParaView that are leading the field of scientific computing and visualization. We have our medical specific applications such as Pulse, SlicerSALT, or Slicer. And you're going to be hearing a lot of this last two from Slicer and SlicerSALT. Without further ado, here's the agenda for today. first, we're going to give an introduction to shape analysis and just introduce some concepts that will be mentioned throughout the webinar. Then we're going to talk about SlicerSALT, that is this platform that we have developed specifically for the distribution of really powerful research shape analysis algorithms to a larger audience. Then we are going to continue with some case study examples. So these are large projects that we have carried out with partners outside of Kitware. So we're going to just introduce a few of them. Then we're going to continue the webinar with a live demo that will showcase some of SlicerSALT's functionality live. And then we're going to have this Q&A session live that I have mentioned before, where hopefully we can have an open discussion where you can inquire, you can ask us your questions about the platform. And we'll finalize the webinar by giving you next steps and what you can do to continue your journey using this tool. But before we go ahead, we're going to start with a poll question. I have spent a few minutes introducing ourselves and our capabilities, but we are interested to hear about you, our audience. So our first poll question is, how will best describe your professional or academic background? So I just launched the poll. Take a minute to read the different questions and reply, and we'll review the answers. All right, so thank you for all of you that have answered questions. So most of our audience is coming from an academic background or from research, but we also have a fair number of engineers and developers and teachers. Welcome. We're so glad you're here. Hopefully you will enjoy the rest of the content. Next slide. Next slide. So the first concept that we have to introduce is shape, obviously, and it refers to an object external form, how it presents itself spatially, how it works. But it's also important to recognize that shape is how we perceive it or recognize it. So if you click through that, Jared. Shapes can be geometric, and these are precise and mathematical, or organic, natural free-form shapes. And we also have examples of shapes in both of these domains that are flat or 2D or 3D and volumetric and 3D. Today, we're going to be concentrating in shape as it is used in healthcare for the design of biomarkers, but understanding shape is really important for a variety of different fields. And here are some examples: architecture, manufacturing, design. And, you know, just to say, like, most of our tools are generic in nature and can be applied to all of these fields, although we're going to be concentrating in healthcare today. Another important concept to the rest of the webinar is what a shape representation is, and it refers to a standardized method for capturing geometric features across a large number of objects. Here we show several examples, both in 2D and 3D. So for example, for 2D, we have point clouds or curves or skeletons or grids. And in 3D, from left to right, we have parametric representations such as an ellipsoid or point distributed models. We have medial representations or skeletal representations. In all of the cases, shape representations are high-dimensional, low-sample size objects where geometries are presented in correspondence. So every representation, when we describe it that way, is analogous from object to object. And thanks to that, we can use many different ways to harness the power of geometric analysis and research. And we'll be happy to discuss a little more further down in the webinar. So with those two concepts introduced, it's important to mention that shape modeling can be used to represent patients' organs or clinical processes, and it can easily integrate with clinical data coming from genomics or self-reported patient information, electronic health data, and so on. So our team has successfully used shape analysis to enable personalized patient care strategies by designing specific biomarkers that can simulate treatment to responses, that can divide different geometric objects depending on pathology or treatment. And ultimately, the most important goal of any shape analysis modeling in healthcare is to improve clinical outcomes via proactive data-driven decision making. And the example on the right of this slide is juxtaposing how shape compares to a less sophisticated geometric biomarker such as volume. So if we just look at the top panel of that figure, we see that volume can characterize some geometric properties of how the heart changes dynamically over a cardiac cycle. There is some compression and then there is some expansion, but it fails to really show the locality of those changes. If we look at the 4D animation, we can see that while the chambers are expanding, the veins are contracting and vice versa. Next slide. So having said that, the next part of our webinar is focused on the technologies that we use to translate all of that powerful research capabilities into a wide network of biomedical researchers. And we do that through SlicerSALT. And the pillar to SlicerSALT is 3D Slicer, which is an open source software that probably many of you know for medical image analysis and visualization. It allows user to load and save data from a wide range of data types. You can do segmentation, registration or superimposition of images in many different ways. You can visualize very complex anatomical structures in it. But perhaps the most powerful capability of Slicer, it includes an extensive suite of analysis and processing functionality. So 3D Slicer is highly customizable and supports a wide range of applications and is really popular among researchers, clinical settings, and medical device companies that incorporate its use into product development. However, the broad capabilities of Slicer are a strength for some, but is also a steep learning curve for other research groups that have very focused goals. So another important pillar of SlicerSALT is this Slicer custom app template that is just a customization wrapper around 3D Slicer we use to create a very custom, lightweight version of Slicer concentrated only in shape analysis. However, anyone can use this to generate their own applications, and just creating your own Slicer app is very easy. You just have to provide a few parameters and you will get your source code. You can customize the appearance and the GUI and the buttons. You can select your own plugins, put your extensions, or develop your own. So it's really simple. Which brings us to SlicerSALT. We use custom app template builders to basically harness the powerful state-of-the-art algorithms within shape analysis research. And we combine that with the high-quality, full-life software capabilities of Kitware to create SlicerSALT, and that is a very robust clearinghouse of powerful shape analysis methods. and it serves many needs. I thought it was important to mention that our group has used SlicerSALT as well as help others use SlicerSALT for designing better fitting implants and developing very detailed anatomical modeling studies that have been used in industry. So we have talked about the different number of technologies. I think it's time to also inquire about what type of technologies do you use in your scientific computing needs. So this is our second poll. We're really interested to hear more about what is interesting or useful to you. So please take a minute to answer. I think Python is going to win this one, closely followed by GPU computing. So here are our results. Most of our attendees use a mix of Python and GPU computing. I will be really interested to hear from those of you that answer mixed stack. So if you feel comfortable, put it in the chat or in the questions. But this is very interesting. Thank you so much for replying. And now we are going to take a deep dive into the capabilities of SlicerSALT through Jared. Jared, take it away.
Yeah, thanks. And as mentioned, we're going to kind of start digging into some specifics. And so if, just to reiterate what was said before, if you have any questions, feel free to drop those in the Q&A and we will do our best to answer them as we go along. Yeah, so I'm just going to get into a few of the specific modules that make up the functionality that's packaged in SlicerSALT. These are going to kind of be organized in 3 different categories. So first is shape representations. And so this is how you take your data, whatever it is, and get it into a form where you can start doing some of the shape analysis we've been talking about. The second category are going to be those analysis functionalities. So now that you have your shapes represented somehow, what can you actually learn from that and how can you do it? And then finally, a few in the miscellaneous category, which are just some things that kind of support the broader goals of SlicerSALT. So the first representation that we're going to talk about is SVARM PDM. And so you may have heard Bea mentioned earlier, the PDM, a point distribution model. This basically in 3D just means a set of points on the surface of the object. And so SVARM PDM specifically uses a spherical harmonics-based analysis to do this. So it takes your shapes, maps them to a sphere, and then uses that to fit a nice mesh to that. And one of the strengths of SVARM PDM is that for a lot of objects with spherical topology, so this is just an object that's just kind of a blob shape, it doesn't have any holes, it's just one solid thing. This tends to work fairly well out of the box and produce nice meshes that will be in correspondence across the population. And so when we're talking about representations, correspondence is really one of the underlying goals, which is to make sure that your representations for your population of objects all have, if you're using boundary points, all have the same number of points, and those points are in the same anatomical locations across all of your objects, because most of our shape analysis methods rely on having that specific kind of representation. And so SVARM, like I mentioned, for a lot of objects tends to work fairly well out of the box. In the cases where it doesn't, we have some information and some tools to try to improve that. But SVARM is not always the correct fit. So we'll talk about a few alternatives. The first is a registration-based correspondence. And so this is really best for if you have objects that are more complex geometrically, or if they have non-spherical topology. So if you have things with a hole in it. This essentially, instead of using the spherical mapping we talked about before, it relies on you having a nice template of the object that has some nice mesh properties. So here for this femur, we're showing this one at the top, which is, you can see the triangulation on the mesh is fairly regular. The points are well spread. So this is kind of a nice looking mesh. And then it can use a surface to surface registration technique to deform that template geometry to match the geometry of each of the other individual objects in the population. So that would be these other three femurs down at the bottom. And then once you've deformed it to match, the points can be transferred from your template onto each of the individual objects. And so, this doesn't, your input meshes can have, a completely different number of points. Everything after this analysis will all have the same number of points as the template. And so it can be a useful thing to try if some of the kind of more standard things like Swarm PDM don't work on your data for whatever reason. So the next is a completely different kind of representation. So instead of boundary points, this is something called we call a skeletal model or an SREP. And this represents an object not by a set of points on the boundary, but by a skeleton, which you can kind of see here as the kind of, for a 3D object, is kind of a surface that goes roughly through the middle of it. And then these vectors coming off of that surface that go up and touch the boundary that we call spokes. And so this is different from the boundary point models in that it represents not just the exterior of the object, but the object's interior as well, which can be desirable for certain applications. SREPs are also very good for thin objects because the thinner an object is, the more closely related the top and bottom opposing points of that object are. And that relationship is captured much more directly in skeletal models than in surface models. But yeah, so it can be useful for those applications, but the SREP fitting can be a little more finicky than some of the other models we've talked about, although we have in the recent SlicerSALT 6.0 release included a new SREP fitting method that we've seen some definite improvements with over previous implementations. And then finally, the last representation we're going to talk about is kind of different from the others, and that the others we're talking about fitting to a population of objects at a single time point each. So in the first example, a bunch of femurs or a bunch of hippocampi or something like that. We also have support for regression models, which are used to analyze shapes over time. And so here we're seeing an example of brain growth over several years. So we can, down at the bottom, you're kind of seeing where we have these 4 discrete time points, brain models from MRI probably, and then we can fit a continuous sequence to those and generate the intermediate estimates of what the shape was as the growth was happening. And then you can see in the top right as kind of going through that series of shapes is to see the brain growth. And the color on that model is showing velocity. So you can see that the growth starts out very high when the person is younger, and it kind of tapers off as they get older. And so this could be useful for longitudinal studies, so looking at shape changes over relatively long periods of time, or as you saw in a previous slide, looking at a beating heart model, it can also be used for much shorter time periods. So if you have things like a beating heart or a respiration where you're having motion in the body, this can be used to represent those. So that covers the representations that we're going to talk about. So now I'm going to get into some various types of analysis you can do on those representations. So the first of those is called Shape Variation Analyzer. And if you're familiar with principal component analysis, that's basically what this module is doing for you. But if once you have your set of representations, this will compute a mean shape. So if you want to look at what the overall population mean is and modes of variation. And so that's what you're seeing here on the right are animations going through these modes of variation for a population of mandibular condyles. And basically what this means is that it's trying to, without getting too technical, these shapes live in a high dimensional shape space, and this is trying to find lines going through that space that best capture the variation of your population. And as you move along that line, you can take samples from it and generate these animations, which you're seeing here. And so the top one you're seeing kind of, there's a little bit of a twisting motion, and you're also losing size a little bit. And so that would be in the population of objects being analyzed here, that would be the most, the type of variation that explains the most of the difference between the the individuals in the population. And the second is kind of this very dramatic loss of volume. I think this was actually modeling bone loss in this population. And so that you can really get a good look at that type of variation in your population. So the second analysis module is doing covariate significance testing. And what this is doing is if you have not just shape data, but you also have additional clinical or other types of covariates. So, for example, if you have a population of hippocampi, and for each member of the population, you may have whether they have Alzheimer's disease or not, or other types of biomarkers. This will compute correlations between each of those individual covariates and the shape itself. And so this is lets you understand how changes in the shape correlate with these other biomarkers. So again, an example of you have hippocampi with Alzheimer's disease, you may see that in a particular part of the hippocampus, you're getting a significant amount of change because you're going to be losing mass because it's a degenerative disease, you're losing brain matter. Here, this is just an example of a p-value map that you get out of this. So for every point on the surface of the object, you get a p-value that basically tells you whether you get a p-value, and then you can threshold that to determine where on the surface there is statistically significant correlation. This is just from a toy example where we have a population of ellipsoids that have these bumps at different locations, and you can see we're able to recover that from the data nicely there. So the next module is called distance-weighted discrimination. So this is, if you're familiar with traditional techniques like support vector machines, that this is doing something similar. So it's computing a classifier to tell two classes of objects apart. This distance-weighted discrimination is a method like a support vector machine, but it's more suited for techniques where you have very high dimensional data, like in shape analysis. So this is good for, again, if you have two groups in a population, like diseased and control, for being able to differentiate between them and to try to understand the difference between those two populations. And so again, we're seeing a condyle here like we did in the shape variation analyzer slide, but instead of moving along these modes of variation, we're moving along a line in this space between one class and another. And so you can actually see the represented on the shape how these two populations differ. And so this can be a very powerful tool for understanding the population, or in terms of this visualization, or if you just want to build a classifier to do something like diagnosis, to be able to tell the two populations apart. And we also have support for deep learning models in SlicerSALT. So right now we have a couple of different models that are packaged with SALT. One is specifically for doing this dental analysis of dental scans that you see on the right here, where it is taking that as input and using a deep learning segmentation method to segment the teeth on this model. We also have another model that is designed for to work on other types of shapes, not just dental specific, but it essentially, without getting into too much detail, can convert a shape representation into a form where it can be used in traditional 2D image-based deep learning. So we currently package PyTorch and a few related PyTorch-based libraries in SlicerSALT. But if you had models in something like TensorFlow that you really wanted to deploy, then we could work with you to get that worked out. And so next, we're going to move on to a few kind of miscellaneous features of SALT. So one is, we've talked about all these representations and analysis, but how do you get your data into SALT to actually do some of this analysis? And so we have a data importer module that can read in both segmentations, both in binary image volume format, or if you have meshes from your segmentations. And it can do a variety of different quality control things automatically for you. So if you're inputting a bunch of meshes, it can make sure that they all have the same topology. So there's not a couple that have holes in them when they're supposed to all be watertight. Or if you're um, again, if you're doing analysis of subcortical brain structures and you have an image where you have both of the hippocampi segmented and you load in a bunch of images, but one of them only has one label instead of two for the left and right hippocampus, then this would be able to flag that for you. So it's just there for doing quality control and making sure that all of your data is in a good state so that you can run some of this analysis we've talked about. Shape Population Viewer is another very useful tool for at various stages in this pipeline, you may want to visualize the data, and again, for quality control purposes, to make sure that everything looks all right. So this lets you load in a bunch of, in this case, femur meshes at once and visualize them all together. It's interactive, so you can translate and rotate things around, and they will all move at the same time. And this can help you make sure that things are aligned, things are in correspondence, there aren't any that meshes that have any major problems with them. And this works for PDMs. You can load in SREPs for this, and you can load in time series and watch them all animate over time together. And finally, there is a pipeline functionality built into Slicer and SlicerSALT that lets you build out custom workflows and deploy them in such a way that they're easier to use. And so this image here on the right may be a little small, but bear with me. I'm going to kind of step through it in a little more detail. But first, you start with your input. So you prescribe, okay, this is the type of input data I need. So in this case, it needs a mesh as input. And this is building a pipeline for fitting SREPs to an input mesh. So you have a mesh, then you basically can, in this graphical user interface, select a number of modules, one after the other, that will be run in sequence. So first, we have an SREP creator module that is just basically takes in an input mesh and does some analysis to fit and do an initial skeletal model for that. And so here you can see that it pulls up that module and all of its parameters. But you also can see here that the input to this, one of the inputs, is this initial input to the whole pipeline. And so that's how it's kind of creating this end-to-end workflow that you don't have to do any, once the pipeline is generated, you don't have to do any intermediate analysis. And moving on, after you've created the initial SREP, there's a refinement step that needs two inputs. One is again, the original mesh that you input in. One is this output of the previous step. And so this, again, will let you set those inputs up correctly, has some additional parameters that you can set if you want. And then you can specify what the ultimate output values from this pipeline are. In this case, it's just the final SREP. And so once you've got this built, it is not just a pipeline that's saved on your local copy of SlicerSALT. It can actually be saved out as a 3D slicer module. You can, if it's analysis that you want to deploy locally within your own company or within your lab, it's easy to distribute. Or if it's something that you want to make available to the public, like if you use this analysis for a paper and want to support more reproducible science, then you can publish the pipeline that you used, and others can run that same analysis on their own data using their own copy of SlicerSALT.
So Jarrett, we have a number of questions in the Q&A that I think we should address before moving on, as they pertain to the different functionalities. First, when I asked what type of mixed technologies you use in the previous poll, I was curious to know what people that replied other. We actually have one attendee that uses Blender within their scientific computing framework, which is really interesting. It's another really great tool, open source tool for mesh modeling. We have a question from Amy from Brown, and she's asking what kind of heuristics are used in spherical harmonic correspondence to show goodness of representation across all of our different representations. And she was asking, can a unified metric be analyzed to quantify the best model for a data set?
to quantify the best model for a data set, that's a very difficult question. There's no, I think, single metric that can be used because it's going to depend not just on what type of representation you're doing, but also what type of analysis you want to do. So models that are best for differentiating between two populations are not necessarily also going to be the best for give you the most compact representation when you do like shape variation analysis. When you're doing principal component analysis and want to look at variations within that population, there could be different features that you want. So it's yeah, that's there's not really a single good answer to that. If you like specifically with SVARM and the spherical harmonics, if you just want to um, be able to look at how well you're doing in terms of correspondence and that kind of thing, then like Shape Population Viewer, which we talked about and which I'm going to show in the demo later, is a useful tool for being able to do that.
Yep. All right. So Akashavu is asking, in the representation part, break growth is biomechanically possible. I can take that one, Jarrett. So our shape regression algorithm, the only thing that we use is geometry change. However, we have had success using geometric change as a proxy for strain, just based on the level of deformation that happens from one time point to the next. However, when you think about biomechanical, like, when we were talking about simulation of physics and fluids and stuff, that type of thing, this is not included in our toolbox, although our toolbox kind of like outputs data in very generic ways, so it could be ingested by other open source platforms such as SOFA. All right, so the next question is from Chimanga Chizuo. And the question is, this will be really interesting for mineral resource modeling. I use -VTK. Is there a way to integrate in SlicerSALT with -VTK to take advantage of the regression modeling and time series in the -VTK app? Jarrett?
So I'm not 100% familiar with -VTK, but so Slicer and Slicer,
a Java wrapper for VTK.
yeah, I mean, Slicer and SlicerSALT are one of the core technologies that they're built on is VTK. So they use VTK for all the visualization, all of the mesh data structures are VTK based. And so, I don't know exactly what format the regression modeling is output from that, but if it's based on VTK, then we could certainly easily create a wrapper to ingest it into SlicerSALT and work with it from there. Yeah, so Slicer, some of the regression tools in SlicerSALT work with Slicer's sequences functionality, which is basically Slicer's inbuilt support for temporal data. And so if there's not already a bridge between -VTK formats and that, because it's all based on VTK, I imagine it would not be too difficult to get up and running.
Questions continue streaming, so I'm going to take one more, and then we'll do our best to address the rest in the Q&A section at the end. So Shintanu Bailur is asking, is it required to register a template to a data set of shapes before running a statistical model, such as distance-weighted discrimination for successful classification? This goes back to Jared's answer to Amy's question. It really depends what you're trying to measure. Sometimes if what you're trying to measure is shape change, just pure geometric change, yes, registration to a template is important. Sometimes we even do, and all of these modules that we have described in this section are not exhaustive. We have many more, but one of them is Procrastus alignment, which can be used to align to a template or anything else as far as everything is in correspondence. And you can also remove scale, because scale is a big confounding factor when you're doing shape analysis exploration at the population level. So, but kind of like the too long didn't read answer to that is really depends. Like sometimes we cannot do that alignment when we're looking at displacements, for example. So it really depends. All right, Jared, you want to take the poll?
Sure. So yeah, we talked about a lot of kind of representations, and we're going to next we're going to start moving into some case studies where we talk about some concrete examples of studies we've done with SlicerSALT. But before we get to that, we were interested in what types of data are you working with, and specifically if you're working in the medical field, what are you working with neurological data, are you working with cardiac data, that kind of thing. So I'm going to go ahead and launch this poll. Yeah, so we've done work in a lot of different areas. So I think we're going to be talking about examples of the first three of these categories. So we're going to talk about nervous system, cardiovascular system, and musculoskeletal. But
All right, and then share results.
Yeah, so it looks like the majority are musculoskeletal, which a lot of our applications as well have been musculoskeletal. So I think that makes sense. There's also some cardiovascular, a little bit of nervous system and digestive system, and also a couple of other. And so for the others, especially, I'd be interested if you want to drop in the chat or the Q&A what other types of data you are working with. That would be interesting information. But yeah, with that, I think we are ready to move on to case study examples, where I'll turn it back over to Bea.
All right, so we have so far covered a lot of technicalities and what SlicerSALT is, what it can do, but we also wanted to take a moment to show you a few exemplary studies that we have carried out. Next slide. So very important to say that all of the small studies we're going to show here showcasing SlicerSALT's functionality have been done in collaboration as part of larger studies and in collaboration with academic partners. We feel really grateful to them. All of them have been published, are in the public domain. So if any of you have any specific questions, feel free to reach out to Jared or me for further information on them. So our first case study, the main goal was so we were interested to see how the tricuspid valve, here pictured on the left, is changing during hypoplastic left heart syndrome. And for that, we need to find a way to consistently represent it across individuals. We did that with SWARM, that you have heard about already. And what we did for this specific example is we fit 3 different PDMs to each one of the leaflets, anterior, posterior, and septal, to the tricuspid valve. So that became our data object of study for the rest of the analysis. So once we had all of our data objects represented in a consistent way, we decided to run a study where we did shape space exploration over a large population of individuals. I have to say that all of the subjects that we used to generate these results had hypoplastic left heart syndrome. But the 2 different strata that we had in that population is individuals that had different levels of tricuspid regurgitation. So what happens in these individuals, and I haven't mentioned this, is they are born with a non-functional left side of their heart. So the only functional chamber is on the right. So the tricuspid valve, that is the valve that connects the atria and the valve in the right side of the heart, is the only functional valve. Many of them end up having valve failure later in life, despite many surgeries and interventions. So we are interested to know what are geometric features differentiate people that do better with all of these treatments and people that do poorly and have higher tricuspid regurgitation. So for these, we just run our shape variation analyzer. And what we see here is we're displaying the average shape of this tricuspid valve representations and all of the different main axes of variation. So we see very clearly the first principal component is scale, which is reasonable finding in a population of pediatric patients. But then interestingly, like the second and subsequent principal components showed variation in the septal leaflet. And this was this was a very interesting finding because the septal wall is the one that divides the left and the right sides of the heart. So is really that area that is not really connected to the dynamic movement of the left chamber. So this was an interesting finding for us.
Yeah, and just to break in really quickly, we had a question about what kind of data this is from. This is from ultrasound
Yeah,
data.
this is from transesophageal ultrasound. Another thing that we did is we followed our PCA analysis with distance weighted discrimination, and we have talked about this. In particular, we were interested to see the geometric features that differentiated between individuals that had good functional data, so mild tricuspid regurgitation, to individuals that had very severe tricuspid regurgitation. And what you see here is as walking, after we found the best separating hyperplane between these two populations, thanks to the ODD, we are able to take the orthogonal direction to basically walk from like mild disease to more severe disease. And we actually found that cases that had mild regurgitation had more billow, which is like the valve is kind of like bulging into the right ventricle. But for those that had very severe regurgitation, there is a bulging or a tenting in the valve. So this triggered more questions within our clinical collaborators, and they're starting to look into like all the papillary muscles that attach to the tricuspid valve. Our next case study is on musculoskeletal, a small pilot for a musculoskeletal application. This one in particular was looking at scoliosis, and scoliosis is just condition that causes abnormal sideways deformations of the spine in children. It can affect anyone of any age, but is more prevalent in kids. And right now, because of radiation concerns, scoliosis is diagnosed in a 3D problem with a 2D modality. They just do x-rays in children. Also, because of these radiation concerns, there is not an understanding on how a healthy spine grows. So for these, we actually found a few sparse observations in 3D for all of these growing spines. All of these are coming from different individuals. That's why you see the variation there. But and what we did is we used our regression algorithms, which some people have asked about, to basically create a continuous deformation across the entire 0 to 15 years of age span in order to create very age-matched controls for all of our scoliosis patients. Next slide. So this is how our different observations look in space if we're just representing them by their volume. So you can see the growth of all of these. However, it's very difficult to tell what happens between them. This is just kind of like our estimation just by putting a line between all the different volume metrics here. So thanks to our regression algorithms, we're able to compute this deformation, continuous deformation. And then thanks to that representation, we are able to sample as many points as we want in between, creating a very, very dense population of growing samples. This is just in 2D, but if we go to the full model in 4D, we actually see we see the whole spectrum of information that we get from this representation, which is thanks to this continuous evolution, we are able to see that there is a fast growth in the inferior superior axis earlier in life, and then the shape model proceeds to incorporate geometric changes that are more complex, such as lordosis. There's that curving of the spine and so on. Next slide. Our final study is a study in neuroimaging. This is just a larger project that investigate how autism changes subcortical structures in children. And for these, our partners at UNC collected MRIs on 177 6-month autistic siblings of kids that had a diagnosis for autism. And the whole idea is to understand what are the geometric features. Sorry for the siren. The geometric features that differentiate kids that go on and develop autism and those that do not develop autism. This will facilitate, the hope for this study is to facilitate interventions early on. And the reason why we did this analysis in 6-month-olds is because as part of this larger study, there were cognitive metrics that were collected, and this is where they first saw that there was some cognitive decline in some of these kids that ended up developing autism. So our collaborators just wanted to see if there are any specific geometric features that are associated to that. And we use SREPs as our representation because we tried other representations within our stack, such as SPARM PDM and so on, and we weren't able to see good results. And we have some more information in the next slide. This shape, so right now we were able, so what we did is we fit SREPs, we ran DWD. Our DWD classifiers are completely agnostic of representation, and we run it through these two classes of kids that go on and develop autism and kids that do not. And what we discovered is that there are significant shape differences between the two populations, although we don't have a visualization yet of what those means. But SREPs in this particular example outperform all the rest of the applications. Before we go into the demo, do we have any questions from the audience that we want to address?
I don't think we have any new ones since the last time.
So I imagine James was asking, is this from CT on the spinal study? Yes, I didn't mention that, James, but yes, all of those samples for our observations were coming from computed tomography on children. We also have a question on logistics. Is it possible to install any of the features discussed today as standalone Python modules, or is it possible to run SlicerSALT in batch mode through the terminal? The answer is yes. SlicerSALT is based on 3D Slicer, and 3D Slicer has an option to launch modules without triggering the GUI. And we include information about that, in particular in our SPARM PDM tutorials.
Yeah, and it's also, we can mention that a lot of the, I don't want to say all, but most of the methods in SlicerSALT are also available in the 3D Slicer extension index because they're all designed as 3D Slicer modules. So that's another option if you're looking just for a specific piece of SlicerSALT.
And I would like to address our remaining question from the previous section. So he's saying, when using the registration-based correspondent for bone models, for instance, are the anatomical landmarks well recognized? So the answer to that is, if there are analogous geometric features, they will be, the registration will pick them up and will use them as drivers for that fitting. Yeah. All right.
All right, then I will go ahead and get started with the demo. Yep, so we should be seeing SlicerSALT now. Yep. So this is, so I'm going to work through just a simple example of kind of starting with a new data set and doing some initial exploration. So this is, we're not going to go through every module available. This is just kind of a way to kind of bootstrap some understanding when you have a new data set. So when SALT launches, it starts on the home module. And one of the things in the home module is over here on the left. There's kind of a few suggestions of how you can get started, what what general order you want to do things in. And so the first thing we are going to do is to do the data importer. So you can either click here. This is actually a link that will launch the data importer module, or you can go up here to, and the first category, the first thing in the list is the data importer. So
we actually don't
yes,
see the pop-ups.
don't see pop-ups. Okay,
Yeah.
good to know. Okay, so yeah, so I'm guessing if I click this, you're not going to see the file chooser either. Okay, that's fine. Yeah, so in the data importer, basically, there are a few different options. You can import from a directory of files. You can import from a CSV file. So if you just have a comma separated list of the files you want to import, or SlicerSALT also supports, directly supports the FreeSurfer file structure. So if you export data from FreeSurfer, which is a common tool for doing analysis of brain images, it will export into a certain data structure that SlicerSALT can automatically parse for you. But here I just have a folder of segmentations and stored as binary images. So I've got that folder chosen. For color table, if there's a specific color map you want to use, you can choose that, but I'm going to skip that. You can either input volumes or models. So models in this case would be meshes, but these are binary images, so these are volumes. And then I'm just going to hit import. And so it'll take a few seconds depending on how much data you have. We're loading 25 scans right now. And so what you'll see is that it will choose the first thing it loads as kind of a template, and it's going to make sure that all of your other subjects match the template. So they're consistent in terms of topology, in terms of the number of segments in the image, and that kind of thing. And so it is just visualizing one by default, but we can go and see all the different ones that are loaded. And we do see that there is one that has an inconsistency. So that is being flagged here in the UI. And so, if this could be, so it's saying that its topology is a torus. So basically it has a hole in it. And so, this is most commonly in this scenario is going to be because there's a hole in the segmentation that just didn't get filled in. And so, you may want to analyze this particular segmentation, see if you can figure out what's going wrong. This would be a case where even though SlicerSALT is built on 3D Slicer, because it's kind of stripped down to just the things necessary for doing shape analysis, some of the segmentation tools in Slicer are not available in SALT. So this may be a case where you would want to load this into 3D Slicer. But in any case, so once you're happy with that, you can kind of select all of the data that you want here. I'm just for expedience's sake, just going to ignore this one that is inconsistent. And so I've selected the rest of them. Here all look good. And then you can choose a folder to export. And so the data structure that you're exporting here will be set up specifically for running through SVARM PDM. And so I've named this SVARM input, and then I can hit this button to generate that data structure. So the next thing to do after you've got the data quality controlled would be to, in this case, run SVARM PDM. And so again, SVARM has an input and an output directory. So I've just got SVARM input and SVARM output directories selected. I could go and SVARM PDM runs in several steps. And so for each of those steps, we have little boxes that are collapsed by default, but have some advanced parameters. So if you run it and things don't go well, you may want to come in and tweak some of these parameters. These are all described in the SlicerSALT documentation. But in any case, you would just make any changes you want and hit Run Shape Analysis module. So I'm not going to do that live. We've made some improvements recently in SALT to how efficient SVARM PDM is. It's now quite a bit faster than it used to be, but it's still not going to be able to run 25 cases in real time. So instead, I've already got a set of shapes generated, and so I'm going to move on to the next step, which is Shape Population Viewer. And so this is useful after doing SVARM to visualize the correspondence and make sure that everything looks okay. And so here I'm just going to open a set of VTK files, which is the output format from SVARM. And you can't see, but I just selected a bunch in a file browser and clicked open. And so here, again, are all of those shapes after they've run through SVARM PDM. By default, it's colored by normal magnitude probably. So SWARM, because it's doing a spherical mapping, gives two parameters which are useful for looking at and examining the correspondence. And essentially, they're called phi and theta, and it's essentially, think of it as like a longitude and latitude on that spherical mapping. So I can choose phi, and I can see that all of the models seem to be in good correspondence. So basically, you want to see the same colors at the same rough anatomical locations in every example. And so everything looks good for that one. And if I go to theta, I can see that there's one that actually had an issue. So it's kind of 180 degree flipped from the rest of them. And again, this is something that it can happen with Swarm PDM. There's actually an option you can go in and select to flip the parameterization that can help solve some of these problems. But again, I'm not going to do that live. But once I've confirmed that everything looks in good correspondence, I'm going to move on to the shape, the shape variation analyzer. It's called population analysis here, but this is going to do the PCA analysis we talked about before. So the input for this is a CSV file. It has some tools to help you automatically generate a CSV file in the right format from just a folder or multiple folders of shapes. But I've already got one created, so I'm just going to go ahead and put that in. And once you've got the CSV file selected, just hit process and export. And so this, by default, will show you your mean shape here in this 3D window. And on the right, if you're familiar with PCA analysis, you're essentially getting a scree plot. So this is showing the modes of variation and how much of the total variance they capture. And so you can see here that the first mode of variation is capturing about 56% of the variation in the data. And if you move these sliders down here in the bottom left, you can actually move along those modes of variation to kind of recreate the animations like I showed earlier. So here I can kind of move in the different directions along this mode of variation, and we can see that there's some it's hard to say exactly what's happening. There's some lengthening of the part of the shaft that we're getting here. There's also a change in the size of the trochanters. So there's a few different things happening in this mode of variation. The second mode of variation is about 20% of the data. And again, we can see here, this is just very much just kind of a general scaling. So people with larger or smaller femurs. And we can continue going through these and looking at what variation is explained by those. There's also, we can project the shapes onto essentially the space of the first two principal components. And so that's available here in this projection chart. And it plots where all of the different shapes project onto this plane. And this can be useful for looking for clusters or outliers. And so you can see here most of the data, actually this is a very light color, so I don't know how well it's showing up, but most of the data is in this, can I make this darker? Yeah, okay. So most of the data is showing up kind of down here in the bottom leftish, but there's a few that are kind of out on the outskirts. And if you hover over one of those, it will tell you some information, including the file name of that one. So you can dig into what's going on. You can also click it and it will deform the mesh here in the 3D view to be what that shape is. So I can go and look at what each of these outliers are and see if there's some useful information that can be gained there. Yeah, so I think that is most of what I wanted to cover in the demo. So let me switch back to the slides, and then I will turn it back over to Bea for the closing.
Yeah, so we still have some more questions, but in the interest of time, I wanted to give some more information about what you can do moving forward. However, I will say that, so if you go to the next slide, we have a user forum in SlicerSALT. So if you have, my first step is try it out. We just released the SlicerSALT 6.0. If you go to the GitHub blog, we are giving specifics and all of the new features we have included. I have to say that all of the modules that you have include a tutorial and a sample data button. So that means you can open the module, download sample data, and open the tutorial. So it's going to tell you exactly what to do. But if you have any problems, you can go to the SlicerSALT discourse and ask questions. All of these questions that are here, we'll do our best to maybe answer them if you ask them in the forum. We also provide paid support, like if you are interested in creating your custom application that you have commercial interests or whatever it is, we can create a package to work with you on it, as well as creating custom training courses for your organization. So for any of these, feel free to reach out through our contact page, and we're always really happy to collaborate. And so sorry for going 6 minutes over time, but we get really excited when we're speaking about this project. And thank you so much for all of you and your questions. Has been a very engaged audience. It's great.
Yeah, and so for the people who can maybe stay, we can answer a few more questions. So there was a question on, I mentioned that most modules in SALT are included in the Slicer, but not all of them. Off the top of my head, I can't give you an exhaustive list of the things that aren't in there. It's mostly going to be the newer modules. So we just had a couple of new modules added in SlicerSALT 6.0 that we just haven't had time to push to the extension index yet. But in most cases, unless it's something like the data importer, which is SlicerSALT specific, there's no reason that these can't be pushed to the extension index. It's just sometimes they haven't been yet. But yeah, if there's something specific that isn't that you're interested in using, let us know and we can get it added to the extension index.
Right. Amy, when we started this project, our goal was to have every single module as a Slicer extension. However, for some of them, there were diminishing returns, like we had very specific modules that didn't make sense to push to the extension index. But in any case, maybe you can push some of them to the extension index if you want, for those of them that are not in the extension index. And for the rest of the attendees, the extension index is just the plugin system in Slicer, how you basically install all the custom modules in the library. Yeah, well, we're getting people really like to talk and are thinking the oh, this one I need to address. SlicerSALT is, the question is, does SlicerSALT work better in a specific operating system? We have made an effort to make SlicerSALT absolutely cross-platform. But macOS doesn't include CUDA support, so the deep learning modules are definitely gonna not work there. In macOS in particular.
Yeah, I think there's one specifically that will not work if you don't have CUDA support. I think we have one of the deep learning modules will fall back to PyTorch CPU support if you don't have a GPU, so it can run excuse me, on the CPU, but there is one of them that requires a CUDA GPU.
All right, we could stay here forever, but in the interest of time, we'll close the session. Once again, thank you so much for your engagement and for your questions. Reach out. We are happy to answer more questions offline. And thank you so much. Hopefully we'll see you around for another webinar in the future. Thanks, everyone.
Thanks.